Hello guys, welcome to another video of the course. In this video, we are going to solve the problem number 23 of the chapter 1 and so on. So I try to complete the problems of this chapter in this video. So here is the problem 23. In the circuit of figure P1.23a, this circuit that we have, a resistance-less toroidal winding of 1000 turns is wound on a ferromagnetic toroid of cross-sectional area 2 centimeter square. The core is characterized by the ideal BH relation shown in this figure, the part B of the figure. Yes, we have this BH curve for the material, ideal BH curve. This circuit is excited by a 60 Hz square wave of input voltage Vi. Our amplitude 108 volts. The amplitude is 108. We have a square wave. The frequency is 60 Hertz. So determine the switching instant and sketch the waveforms of the voltage VL, the voltage of the inductor, and the output voltage, the voltage of this resistor. So we don't have the value of the resistance. Is it important or not? Let's check. Here is the problem. Let's copy this image. We have this problem and we have this HP curve for the inductor. So let's consider a simple version first. What is the simple version? I am going to consider input voltage Vi here and one inductor here and a resistor. So let's consider this pH curve with a constant permeability. So as you know, in this case, we have a constant value for inductance. Yes, we have a constant value for inductance. Depending on the value of the permeability and dimensions of the toroid, we can calculate the inductance, that is n to the power 2 divided by reluctance. Anyway, so you know this is a first order circuit, and when we apply a voltage like this to this circuit, depending on the initial value of the inductor current, yes, the I0 is important, we can have this waveform for the output voltage VO. So when we apply this voltage, suppose we have this current, I am going to plot the waveform of the load current IO, and you know that the waveform of the VO is just R times the voltage of VO is just R times IO, a linear relationship. So if we have this I0, when we apply positive DC voltage, we have rise in the value of the current, yes, depending on how much is the value of the time constant. And then when we apply this negative cycle, this is the value of the current waveform. Yes, you solved this problem in electric circuits course. Depending on how much is the value of the time constant, we can calculate this function. This is the output voltage. Also, we know that Vi is equal to VL plus VO, and we can calculate the inductor voltage. So, how we can solve this circuit using the simple order? You can solve this circuit manually, but I am going to use the simple order to explain the details of this problem. So let's generate a new project and save it. This is the problem 22. So ANSYS files, problem 23, excuse me. Save. Let me generate a new simple order design and close this one. From here, we can select basic elements, basic circuit elements, passive elements. We need inductor. So let's zoom. And we need a resistor here. Let's connect. Finally, we need a voltage source, E. So what is the waveform of the voltage source? Is this one. We have this square wave. How we can set the value of E? Here, this is the EMF value, the voltage of the right input voltage that we have here. I am going to use a pin to set the value of this EMF. You can set a constant value here, but in this case, I am going to use a function and set the value of the voltage using a function. So here we should set the value of the voltage. Let's select a time function pulse. Okay. So here we determine the waveform of the input voltage. What is the amplitude? Is 108. What is the frequency? 60. And yes, that's all. Let's press OK. And finally, we need to add ground. From here, we can add ground to solve this problem. So let's set numbers here. Depending on the value of the resistor and inductor that we have here, we can determine the time constant. So what is the time constant for the RL circuit? For the RL circuit, the time constant is equal to L divided by R. The half of time period here is equal to 1 divided by 60. This divided by 2, right? This is 0.0083, or if I multiply this by 183, it is 8.3 milliseconds. So I'm going to consider the time constant equal to 1 millisecond. How we can set it? If we consider the value of the resistance equal to 1 ohm and inductance equal to 1 millihenry. So we can set the value of the time constant. So here 1 millihenry and here 1 ohm. Okay, we can run this simulation. Let's simulate it for 2 electric periods, 2 seconds divided by 60. Okay, so if I run this transient solver, then I can plot the value of the current for the resistance or the value of the voltage. Here we can plot the value of the input voltage and the resistance voltage. So here you can see these waveforms. Here we can set the value of the inductor current, the initial value. If I set the initial value of the current equal to 0 and rerun the solver, we will have these waveforms. This is the voltage V, and this is the waveform of the output voltage. So we have this rise in the value of the resistance voltage. Also, we can calculate the voltage of the inductor. We can plot it L1.V. This is the inductor voltage. Yes. When we change the polarity of the input voltage, we have this jump, this spike in the value of the inductor voltage. The peak value is close to 2 times 108, 216, right? So I need to reduce the time step size of the solver to detect the inductor voltage spike correct. Okay, when we change the polarity of the input voltage. So how we can calculate the voltage waveforms for this case? So let's calculate the voltage waveforms for this case and compare. In this case, what is the value of the inductance? Yes, we don't have a straight BH curve. In this case, we have two operating modes. We have unsaturated core, this region, this line, this one, when the core is not saturated, and the saturated core, these regions. So for the case that the core is not saturated, the reluctance is 0. We have infinite permeability. Yes, H is 0 and this line is in parallel with the B axis. So we have infinite permeability, 0 reluctance. The inductance is infinite, and finally the value of the current in this case is 0, right? The inductance is infinite, the value of the current is 0. When the value of the current is 0, the output voltage is 0 and the inductor voltage is equal to the Vi. So, the second case. In the second case, when the core is saturated, these operating regions, the slope of this line is 0. It means the reluctance is infinite and the inductance is 0. And when the inductance is 0, the value of the voltage, right here, VL is 0 and the VO is equal to VI. And in this case, we have current for the load. But how we can calculate the waveforms and what is the switching instant? So we can consider this. When we apply the voltage here, for example, 108, and consider the 0 time. When we apply 108 volt and the current is 0, so because we have actually this pH curve and we are here, H is 0, you know this equation, E is equal to d lambda dt. The value of the current is 0, the inductance is infinite, and the value of the VO is 0, so VI is equal to VL or d lambda dt or n d phi dt. So in this case that we applied a constant voltage, if we calculate phi considering the previous problem, we have this phi 0 plus integral of from 0 to t vi divided by n dt. Okay, so the value of the flux rise depending on how much time is passed from 0. So in this case, the flux in the core will rise up to this point when we have saturation. And when we have saturation, in this case, the inductance becomes 0, the VL becomes 0, and we will have load current, and the VO will be equal to VI. So here you can see the equation. Yes, we need to consider a steady state case, and here consider this. Suppose we have this jump from negative 108 to 108. In this case that we have this jump, the value of the change in the flux is equal to this one. The value of the change in the flux is 2 times phi saturation. And you know that the saturation flux is 2 times the cross-section area of the toroid times the B sat. The saturation value for the B is 1.5 Tesla. So if you replace this 2 centimeter square in this equation, the change in the flux is equal to 6 times 10 to the power minus 4 Weber. And this is the equation derived by the integral that we wrote. So T, the switching time, times the input voltage, Vi, is equal to N delta phi. So we have delta phi, we have N, we have Vi, we can calculate the switching time Ts. So here, as you can see, we calculated the switching time equal to 5.56. So this is the case. When we apply this voltage, waveform, okay, this square wave, in this instant, when the polarity of the input voltage changes, this is Vi and this is VL inductor. Here, the inductor voltage, this is 0, and also this is the x-axis, the time. Here, the inductor voltage is 0, yes, because we have a current in the resistance. And then when we apply 108 and we have change in the polarity of the input voltage, the value of the load current becomes 0, and we have this voltage on inductor until saturation of the core. Then when saturation occurs, the inductor voltage becomes 0, right? And so on. So for the next polarity change, again, we have this voltage for the inductor and so on. This is the switching, right? Instant that we calculated it here. And what is the load voltage? The load voltage is this one. Here in this interval is 0, then is equal to this one. Again, it is 0, and then it will be equal to this one, and so on. So how we can solve this circuit using the simpler to verify is our calculations correct or not, right? Did we model these two operating modes correct or not? We don't have a linear inductance here. How we can calculate this inductance, this complex model for the inductance is simpler. Here, as you can see, I generated these waveforms. This is the input voltage. This is the voltage of the inductor. Yes, and this is for the load. These waveforms that we discussed here. So, in the new case, we don't have this simple case. Let me copy this and paste. You can generate also these models. In this case, we can specify a nonlinear behavior for the inductance. Here we have these two cases. We can specify inductance if we have a constant value for the inductance, the first case, or we can specify the inductance current as a function of its flux linkage. Okay, so here is the BH characteristic of the inductor. Here we have H and here we have P. So this is 1.5 Tesla. We have this unsaturated core region and this is negative 1.5 Tesla. First, we should translate this to this for the inductor. This is inductor current and this is inductor flux linkage, lambda or psi, as denoted here. This is psi is the flux linkage of the inductor. So how we can translate this? We know that H is Ni divided by L, and B, we can translate it to psi, that is equal to N times phi, or n b a. We have a, we have n, and we have b. That is 1.5 Tesla. So we will have this curve. How much is the psi for the saturation, right, region is equal to, I can write 1.5 Tesla times 2 e minus 4 times the number of turns, that is 1000. It will be equal to 0.3 Weber. Okay, this is 0.3 Weber. So here is the case, but in this figure, the flux linkage is a function of I. In the software, we should specify this function. The current is a function of the flux linkage. So if we have a one-to-one function, injective function, we can change the order easily. But is this a one-to-one function? No. Because here, for this case, right, if we intersect this region with this line, we have infinite points. So how we can change this function to a one by one function? Again, we can consider this case. We can consider a very low slope here, okay, and a very low slope for these two lines. Like before that, we considered that epsilon in MATLAB for the previous problem. So this is just because of numerical calculations. Otherwise, we cannot simulate this complex behavior in the software. So I'm going to consider this waveform for the psi versus I, and then we can calculate psi inverse, or actually this function I as a function of psi. So how we can define this function? We can define it like this. Let's define a data set. This will be our new function. This is the value of the psi. This is I. So we will define a function like this. A function like this. Okay. So here, this is 0.3 Weber, and this is 0.3 Weber. So we can define this when this is, for example, negative is equal to negative 100 or negative 1000. This can be equal to 0.30001. When this is equal to negative 1 e minus 2, excuse me, the x is the flux linkage. So let me copy this. I can this equal to negative 100. When this is equal to negative 0.3, 1 e minus 2, negative 1, the value of the current, this point, we have defined 1 point here, 1 point here, another point here, and another point here. So we can consider 0.3 here, 1 e minus 2, and 100 here for the current and this value. Okay, we have defined this function. Consider these very low numbers for the current and flux. Otherwise, we cannot define this function correct. So we defined a nonlinear inductor here. The current, its current is a function of its flux linkage. In this case, the value of the resistance is not important. So let me consider 10 because we should keep the value of the current below this number 100, just that we defined here. You can extend the region and let's run the analysis. But in this case, because we have switchings, the time step for the simulation should be very low to calculate the switching instances correct. So here I consider 0.1 microsecond and 1 microsecond here. So let's run the simulation and check quantities. Here is the waveform. The waveform of the here this is just because of the dot point for the input voltage. Here the dot point is here and here is the dot point. Just I multiply this E1 by -1, apply. So now this is the input voltage. This is the voltage of the resistor and this is the voltage of the inductor. So let me simulate 5 electric periods to pass transients. As you know, here we are using a transient solver and we set the initial value of the inductor current equal to 0 because we are going to pass transient and calculate the waveforms, these waveforms for the steady state. Yes, we need to consider this stop time for the simulation. So let's run and then we can focus right for the last electric period after passing transients. So here let's zoom. In this case, this is the input voltage, inductor, and the resistor, these waveforms. So you can see how the ANSYS Simplorer software is powerful, right? We can model these complex BH curves for materials and calculate these graphs. However, we analyzed and manually calculated the switching time, that is 5.56 milliseconds. Let's check in the software. If I add this X marker here for the inductor and add another X marker here, how much is the switching instance? 5.5856. That is very close, this one, this waveform. So you can realize the important point of this problem, what are operating modes, and so on. Also, you can generate this graph. You can plot the L1, right? The L1, we can here, we can select this, select the flux linkage. I am going to have the flux linkage of the coil in the outputs also. So let's analyze the problem again. I want to plot the flux linkage of the inductor L1 dot psi, the flux linkage. So here you can see the waveform of the flux linkage. Very beautiful, right? As we discussed, when we change the polarity of the input voltage, the flux linkage increases linearly up to saturation. When we have saturation, the inductor voltage becomes zero and we have current in the load. We used this equation, right? This integral equation to calculate the switching time. Perfect software, very powerful, right? We can do such simulations. So this is the aim of the course, not just solving these problems analytically, but also using advanced software to learn the concepts in deep so you can redo this simulation and interpret the results. Anyway, let's continue for the next problem. Okay, problem 24. Suppose that the soft iron keeper in the permanent magnet of example 1.8 is reinserted. Determine the flux density in the magnet if the recoil permeability of the magnet material is 4 times mu 0. So to answer this problem, first, let's review example 1.8. Here is the example 1.8. In this example, we have this structure. This is a hard iron, the magnet material, and this is soft iron material, and we have one air gap here. So the operating point of the magnet BM and HM are given. The dimensions of the air gap are given, and we should determine the dimensions of the LM and cross section area of the permanent magnet. So what is the pH curve of the magnet? And the pH curve of the magnet for what region is important, for what quadrant is important. Here in this section, you can read about permanent magnet and the excitation procedure, okay? How we magnetize magnets. So here is the permanent magnet system, and this is the magnetizing process. Yes. So here, if you consider this case, this system, suppose we have this soft iron and this magnet. So if we have this material, this is a soft iron core, and suppose we have a permanent magnet material here, and we have one excitation coil here. Okay, so this is the, for example, the direction of the current. We can connect this terminal to the positive DC link voltage and this one to the negative. This will be the direction of the field generated in this core. If we consider this permeability for the soft iron equal to infinite, we can say that the total magnetomotive force drop occurs on the magnet material. So, for a soft iron material, you checked the HP curve. If this is a soft material, if consider this material instead of magnet a soft material, so this will be the hysteresis loop HB. Let's start from this point. When we increase the value of the current, right, we will move along this direction, and when we reduce the amount of the current, this is return path, right, and so on. This is the hysteresis loop of a soft iron material, and the area of the hysteresis loop is low. But in the case of a permanent magnet, a hard iron, when we start, now consider that this is a PM material, a permanent magnet. When we start from this point and increase the value of the coil current, we increase the value of the H along the magnet, right? For example, up to this point. And when we reduce the amount of the current and consequently reduce the amount of H, this will be the return path. So if we set the value of the current equal to 0, we will have this remanent flux. It is called BR, right? Remanence flux. And again, when we apply current in the negative direction, right, we move in this right direction along this trajectory. So for permanent magnets, this quadrant is important. Again, we can continue, and in this case, the area of the hysteresis loop is high, the hard iron. So now suppose this case, suppose we have magnetized one magnet, and now this is the operating point of the magnet, and we place this magnet in a circuit. Suppose we remove the coil now, okay, and I am going to just consider one air gap here. So let's consider one air gap here instead of this coil. I am going to consider one air gap here, and I want to calculate the field generated in the air gap. So how we can calculate the air gap field? In this case, because we removed the coil and we considered one air gap here, we know that the state of this PM material is here. This is the H and this is the B. So we are here, B, R. So in this case, when we consider this air gap, how much will be the value of the B gap, and H gap? Okay, so this is, again, I explained, this is ideal iron. So in this case, we can use the same equations that we have. Curl of H is equal to 0, this Maxwell equation. So integral of H dot dl is equal to 0. And finally, if we consider this integration path, this one in the middle of the core, we can write this. This is the HM. I am going to consider this reference direction, HM, and this is H gap. So HM times LM plus H gap times gap will be equal to 0. And also, if we consider this equation, you know these equations, divergence of B equal to 0, we can write B magnet times the area of the magnet. This is the cross-sectional area of the magnet. And this is the cross-sectional area of the gap is equal to B gap, A gap. So if we know dimensions, okay, we can specify B gap, and also we can specify H gap and HM. So, but how to calculate? This is the HP curve of the magnet in the second quadrant. Yes. And according to these equations, you can calculate the H inside the magnet. Yes. H inside the magnet. As you can see, H inside the magnet is in opposite direction of H in the air gap. And also we can calculate the value of the B. So HM and BM are operating points, the new state of the material. So I can draw this line. Let's use red color. This is called air gap line. Air gap line or load line, or I think there is another name here, shear line. So when we consider this air gap, the state of the permanent magnet material moves from this point to this point. What is the value of HM here? HM, and the value of PM will be equal to these two numbers. This is the HM and this is the value of BM. Okay. So these two numbers that we have, depending on the dimensions of the air gap, we can calculate. So we derive the equation of this line, and after intersection we can find this point. Yes, we did this before. This is the equation. In this equation, if instead of H gap you write B gap divided by mu 0, and instead of B gap, let me remember this figure. Just I want to rewrite this equation. We have this equation, HM LM plus B gap divided by mu 0 times L gap equal to 0. Instead of B gap, we can write this. Instead of B gap, we can write BM AM divided by the area of the gap, considering this. So we can write HM times LM plus BM, right, times AM divided by A gap. This is L gap divided by mu 0 equal to 0. So this is the equation of this line. So if we have this pH curve for magnet, we can calculate the intersection and finally find the operating point. So dimensions are given dimensions are given in this figure. You can see the length of the magnet, the area of the magnet, and the operating point. So we should reinsert the iron keeper. If we reinsert the iron again here, so the value of the H, the external field, will be equal to 0 for the magnet. It means we have short circuit. We did short circuit here for the magnet. Yes. So in this case, the value of the H will be 0, but what will be the value of the remanence flux for the new case? So this is the BH curve of the magnet. This is H, B, BH curve. So we magnetized the magnet first. We removed the coil. We considered the air gap. And this was the new state of the material. Again, if we reinsert the iron keeper, this will be the return path. Yes. So this is the recoil line. And we not necessarily, right, move in this direction. So if we move this in this direction, this is good because again we get this remanence flux. But for materials, for the permanent materials, depending on the knee point and the HM, the operating point, we can move in this direction, right? This is possible. So in this problem, the slope of the recoil permeability, the recoil line is given here, the recoil permeability. If you look at this graph, yes, we have this situation. If we have the slope of this recoil line, we can find the new operating point, the new value for the remanence flux. So how we can calculate it for our problem? This is the problem. Yes, just equation of this red line. This is the equation of the red line. We know the BM and HM, the operating points. We have these two numbers in this example and we have dimensions. So you have the slope 4 times mu 0. Finally, you can calculate the new value of the BR. I implemented it here, these numbers. So the remanence flux was above 1.2 Tesla, but in this case is 1.16 Tesla. So this is the solution procedure for this important example. So how we can solve a problem with magnets available in the ANSYS Maxwell software. So here I generated a new project. Let me add a Maxwell 2D. Just I want to calculate the field generated by a permanent magnet, a cubic permanent magnet in free air. So let's draw a rectangle here. X size, let's consider 10 millimeters and the Y size equal to 5. So if we magnetize this magnet in X direction, You know that the generated magnetic field by this magnet will be this. Okay, will be in this direction. So this is the generated field. Let's set the material here. I am going to set it equal to alnico 5, the magnet material, and for this material we can look at the properties. So here, materials, alnico 5, the same material that we have here. It's BH curve in the second quadrant. So you can see the BH curve of this material. Okay. And we have this number, magnetic coercivity, the coercive force. You know, what is the coercive force for a magnet? The coercive force is the value of the ampere turn when the value of the B is 0, is this one, Hc. This is coercive force when the value of the B becomes 0. For this material is equal to this one. The unit is Oersted here. And here we have X, Y, and Z component. What are these numbers? You know, we should specify the direction of the magnetization. So for this cubic magnet, is the direction of the magnetization is in X direction or Y direction or any arbitrary direction. So I want to set it in X direction. So the material coordinate system, let's select Cartesian and set this equal to 0. The field will be in the X direction. So yes, let's draw a region, offset equal to 500%. This is a magnet in free air. We need to consider enclosure with these dimensions high enough, more than the maximum size of the magnet. So let's add this boundary condition, select edges and vector potential 0, add solution setup, we can solve the problem. Also, let's select all and apply a mesh operation, let's say 2 millimeters. Analyze. Now we can calculate the magnetic flux density vectors. So here, B, you can see the field generated by this magnet. Let's reduce the spacing and also reduce the size of the vectors. Yes, this is better. So you can see this is the field generated by the magnet. We magnetized the magnet in X direction. So if I magnetize the magnet in Y direction, okay, let's repeat the problem, analyze. You will see that the magnetic field, the flux density vectors will be in the Y direction in this case. Yes. And if I magnetize it in this arbitrary direction, 1 and 1. So in this case, the direction of the magnetic field will be in this direction. So let's repeat the problem, analyze. We can check the generated flux density vectors in this direction. Even you can plot the flux lines. Yes, perfect software, perfect environment to learn these concepts by solving the problem using the finite element method. So now let's plot the magnetic field intensity vectors. So here, let's set the direction of the magnetization in x direction and delete the b. You can follow the b vectors. Let me rerun the simulation. Just I want to explain this important concept that we have. These are flux density vectors of the B. So you can see this pattern. We have this. If you consider this integration line, yes, this loop, the flux density vectors are in this direction, and for the external field in this direction. Okay, we have a right solenoid here. So yes, this is the case that we have for B. But what about H? What about H? For B, if you consider this tube of the flux, if you consider this tube of the flux, if I consider this, if I consider this region, I know that divergence of the B is equal to 0. So the flux entering into this region, right, from here, right, we have the same flux in this direction, and divergence of the B will be equal to 0. This Maxwell equation that we have. But if I delete B and plot H vector, let's reduce the spacing and the size. Spacing, also the size, yes. So you will see this important concept. Let's also use a uniform color. Just I want to visualize it. So this is the H field, the magnetic field intensity, H. And as you can see, if I consider this path, the direction of H inside the magnet is in this direction, and for the external field is also in this direction, right? So if you move counterclockwise along this path here, the field is in opposite direction of your reference direction, and for the external field is in this direction. What is the reason? Because curl of H is equal to 0 in this case. We don't have any free current in this red loop. So the Lm, the length of the flux line in the magnet, times Hm plus the length of the flux line in the gap times H gap will be equal to 0. And we have this equation, this one. As you can see, the magnet field intensity, the field intensity inside the magnet is in opposite direction of the H in the air gap. What we mean by opposite direction? You should consider a reference direction, this green one. So for the external field, if this is in the same direction of the reference loop that we have here, for the next one, is it in the opposite one? So what we mean by the opposite direction is this. So this is important. Okay, so now let's add a new 2D design. I deleted the previous one, Maxwell 2D, to generate the geometry and solve the problem, compare the results with what we have here. So the geometry that I am going to create in the ANSYS Maxwell for this problem is different from the geometry that we have here, because in the problem 25 and problem 26, when we are going to repeat the same finite element calculation, the length of the magnet will be low and we cannot use this geometry. So I will explain. Here, like before, let's add a rectangle. How we can set the dimensions? X size, let's consider width of the magnet plus width of the window plus width of the air gap. Here in this example, we have the cross-section area of the air gap and the cross-section area of the magnet. We don't have the depth of the problem. I consider the depth of the problem equal to 1 centimeter. So this will be equal to the width of the magnet, and this will be equal to the, excuse me, this is width of the air gap, and this is the width of the magnet. So, okay, considering this assumption, the depth of the problem is 1 centimeter. So here, the width of the magnet for this example is 2.105 centimeter. The width of the window, let's consider 15. And the width of the gap, the area of the gap is 2.5. If we consider the depth of the problem equal to 1 centimeter, so the width of air gap will be 2.5 centimeter. So what about the y size? I consider it equal to width of the window plus 2 times width of the yoke. So width of the yoke equal to 3 centimeters. Okay. So what is the width of the yoke? I will explain. Just let me create another rectangle. Here we can set this. This is the position of the corner point, width of the magnet, width of the yoke, and 0. This is width of the window, width of the window. So let's save, then subtract. Okay, so here we have this object, and here are dimensions that I considered. This is width of the magnet. This is width of the yoke. This is width of the yoke. This is width of the window. Also, this is width of the window, a square window. And this is width of the gap. Okay, so the width of the outer rectangle is width of the window plus width of the magnet plus width of the gap. This, right, expression. And the height of the outer rectangle is width of the window plus 2 times width of the yoke. So now I can generate the geometry of the magnet here. So how we can set dimensions? The position, the corner point, this is width of the yoke plus width of the window divided by 2 minus length of the magnet divided by 2. What is the value of the length of the magnet? For this example, example 8 is equal to 6.06 centimeter. So, what is the x size is width of the magnet, the y size is length of the magnet, this magnet. The geometry that we used is different from this one. Because when we consider a low width for magnet, yes, we cannot use this geometry properly for problem 25 and 26. Anyway, so here I select this rectangle object first, rectangle 1, hold the control key and select this one, subtract, but this time we are going to keep the geometry of the magnet, right? We need that, and we are going to define the magnet material and the magnetization on it. So here, clone tool objects before operation. So in this case, this is the rectangle 1 and this is the rectangle 3. So this is the magnet object. Let's change the color to this one. So this is much better. And let's generate the air gap. So here we can set the dimensions. This is width of the magnet plus width of the window. This is width of the yoke plus width of the window divided by 2 minus length of the gap divided by 2 and 0. The length of the gap is equal to 0.5 centimeter. So here, excuse me, it is equal to 0.4 centimeter and I write 0.4. Okay, the x size is width of the gap, the y size is the length of the gap. So we can generate this air gap. And here, let's select this object. Okay, let's select the rectangle 1 first, and for subtract, again I check this option, clone tool objects before operation, because I need to keep this rectangle. So this is the air gap. Let's change the color of the air gap to this one. So we have iron, magnet, air gap. I want to explain one important concept and how our analytic calculations differ from the numerical calculations that we have here. The importance of leakage flux. Okay, so here let's set materials. This is iron, so I'm going to set the material of this object to iron. Okay, cast iron, no, the previous one that we used is this one, and the material of this object to alnico 5. Okay, the same material that we have here, this HB curve, view material. Okay, this is the material, and this is the vacuum. I want to define two air materials, so I will explain later. So let's save the model and draw the region. Offset, let's consider 100% offset. this A region, we can select edges and apply boundary condition, okay, on this edge. So now let's draw two lines in the middle of this magnet and in the middle of the air gap. Here we have the flux density in air gap and flux density in magnet Bm. Also we have Hm and H gap. In this example, it is assumed that Bm is 0.95 Tesla and Hm is negative of 42 kiloampere per meter, this operating point. So here, let's draw a line in the middle of this object, polyline. I write this is polyline of the Bm material. Let's set the dimensions. Here, let's write width of the yoke plus width of the window divided by 2. And this is width of the magnet. Generate a new line in the middle of the air gap. Let's change the name to polyline air gap and set the dimensions. So here we have width of the magnet plus width of the window, and this is plus width of the gap. So here we have these two polylines. Everything is ready. We can run the analysis. So here, let's add the solution setup and also set the magnetization direction of the magnet material in the direction of the y-axis, the coordinate system, Cartesian, and also let's select these objects, right, except this one, this region, and assign mesh operation, right, to solve the problem and calculate flux lines with a good smoothness. So yes, we are ready to run the analysis. Analyze. Now I am going to plot the y component of B on this edge and this edge. So here, let's in the field calculator define this quantity B, select the y component. So this is By. And also let's add H component. Okay, Hy. We need these two. Okay, so simulation completed. Let's plot B vectors on these two edge objects. Yes, you can check the value of the B here and here. This is in the direction of the Y. We can reduce the number of points for better visualization. You can see B vectors and P vectors that we have in the middle of the magnet and in the middle of the air gap. Also, you can visualize H vectors. So this object, this one, field H vector. As you can see here, H vectors are in the same direction. So we discussed this. Let's consider only 5 points. Yes, you can see H vectors here. We know that H gap is much higher than the H of the magnet. Okay, so we have these vectors here. Okay, anyway, Now let's generate this plot. Field report polyline PM by. Okay, this is the y component of flux density along the polyline BM and polyline air gap. Okay, you know the value is negative. Let me multiply this by -1. What is the maximum value here? Is 0.54. And what is the average value here? Point, excuse me, 1.15. What about the value of the H for polyline PM? Is negative, let's calculate the average value, negative 28 kiloampere per meter. But here, when we set the dimensions and when we selected this operating point for the magnet, these values for BM and HM, we calculated these dimensions for the LM and AM. The operating point is this one, not this one. But why we calculated these numbers in the finite element software? So this is the average value of the flux density in the magnet, 1.15. Here we have 0.95. And here the value of the H should be -42. But here is -28. And the same for the maximum or average value of the flux density in air gap. Here the maximum value is 0.54, but here the assumption is to have 0.8 Tesla in the air gap. The reason is leakage flux. If I select all objects and plot flux lines, increase the number of flux lines, let me use this color, increase the number of flux lines to 50. As you can see, we have this leakage flux. Okay, so the flux generated by this magnet is not totally linked, right, in the air gap. We have this flux. So actually, let me copy this image. The magnet in the equivalent circuit, we didn't discuss the equivalent circuit of permanent magnets. The equivalent circuit, the magnetic equivalent circuit of a coil, we have modeled it with a voltage source, the magnetomotive force source. As you saw in the simpler design, here, basic elements, domains, magnetic, we had this source. But also we have this flux source. Okay, so here you can see the value is, the unit is in Weber. In the magnetic equivalent circuit modeling, a permanent magnet is modeled with a current source. Okay, a current source, a flux source. This element that we have here in the simpler. And also here you added a reluctance, right? The reluctance of the iron part in the coil, here we can have this reluctance in parallel with this current source to model the leakage flux, right? This amount of the flux, right, is leakage one. This is leakage one. This flux is not passing through the air gap. So we didn't consider this in this perfect formulation. In this formulation, we assumed that we don't have any leakage flux. And we assumed that the total flux generated by this magnet is passing through the air gap. So we wrote this equation. Okay? We wrote this equation if we have this Bm in the magnet and this in the air gap, phi is constant. Bm Am equal to B gap A gap. We don't have this situation, right? We have leakage flux and only a percentage of this flux is passing through the air gap. We should multiply this side by this factor, KL, leakage, right? Coefficient. That is a number lower than 1 to be perfect. But can we solve this example in ideal case? Just I want to check if our assumptions and calculations are correct. Here in the ANSYS Maxwell model, we have this region, okay? And I defined, let me reduce the number of, or let me delete this. Again, we generate the plot. We have this air gap, we have this region. I am going to define a fictitious material. And I am going to consider the magnetic permeability of the region, the relative permeability of the region, equal to a very low number, close to 0, to suppose that we don't have magnetic flux lines in the region, right? A fictitious material. Just to consider this perfect assumption that we have here, that the total flux generated by the magnet is passing through the air gap. So in this case, I need to set the material of the region again, the vacuum. I clone this material to define a new material. So this is the vacuum one, the fictitious material. So, okay. Now we have this material, and this is the material for the air gap that we have like before. This is the air gap material. So for the vacuum one, the relative permeability is 1. Let's consider it equal to 0.01, a low number. And repeat the analysis. We have a region with a very low magnetic permeability. So the permeability of this iron part is much higher than that. We shouldn't have leakage flux, and consequently we should be able to get these two numbers. So the solution, right, the solver is running, and now we have these results. What is the value here? 0.93. The average value of the flux density in the air gap is 0.77, and here is negative 45, the average value of H in the magnet. So again, if I select all objects and plot flux lines. As you can see, in this case, let's consider 50. We don't have much leakage flux, right? Because we generated a fixed material and the flux generated by the magnet is passing through the air gap. Even if I reduce the permeability of the air gap 0.001, this number, let's rerun the analysis to calculate the operating point of the magnet and compare. So now you can realize the importance of the leakage flux. Okay, in the next chapter we will discuss leakage flux in the model of the transformer, but here just I wanted to explain why you cannot get these two numbers when you solve the problem numerically in the software, because in that model you didn't consider the effect of the leakage flux, and as you can see here, these numbers are now close to what we have. Okay, because we should investigate, we should check whether if we have the exact HP curve here and the HP curve that we have in the ANSYS Maxwell or not. But now we know that these numbers are close to what we have here in this example. So, okay, you can repeat the same example and compare the numbers.